I'm on now? Okay. Okay, so hello. My name is James Sylvester, and today we'll be looking at cutting solutions for complex components. Firstly, we'll have a look at why we section using a wet abrasive cutting, and talk briefly about selecting the correct cut-off wheels to get the best cut and why that is necessary. We'll also discuss different clamping options available and see some real-world examples of clamping done here at Struers. For us to say we have a proper cut, we should meet the criteria shown on the screen. But the main points are absolutely essential, and they are that the specimen must be cool to the touch after cutting and have no thermal or damage or burning to the surface. The sample being cut shouldn't grab the wheel during cutting or cause blocking of the cutting wheel, as nearly all wheel breakages are caused by improper clamping techniques and practices. If we clamp the sample correctly, you stand a better chance of getting your part you need, minimize subsequent grinding operations, and help speed up the throughput and reduce consumables cost through fewer wheel breakages and breakdowns. Here you can see some equipment from 3 different mechanical cutting techniques: a bandsaw, abrasive wet cutting, and precision wet cutting. Abrasive wet cutting is Struers' preferred metallographic cutting technique, as it achieves the most economical cut with the least post-processing times needed to get a true structure. If we look at the surface finish comparison between various types of cutting options, we can see the difference on surface roughness from a bandsaw cut compared to a wet abrasive cut. The bandsawing gives a roughness of more than 30 microns, significantly more than the 5 to 10 microns from abrasive wet cutting. The surface improvement like this can mean a shorter grinding step to remove the mechanical damage to get to the true structure. This is the reason why Struers tend to cut the way we do. The principle of abrasive wet cutting can be seen from this sketch. Some equipment has the cut-off wheel moved into the workpiece at a certain speed and RPM while coolant is added. Others may move the workpiece into the cut-off wheel with the wheel locked in place. The end result will be the same, with the abrasive wheel wearing away a thin section in the workpiece to carry out the cutting operation. The cutting wheel consists of abrasives, bonding material, and pores. Deliberate changes to the bond strength and the pore spacing change the properties of the cutting wheel to enable the wider range of hardness of material to be cut cleanly and efficiently. These differences in pore spacing and bond strength are also within the wheels themselves, which ensure a reproducible and consistent cut every time. It's all too easy to assume that all cutting wheels are equal. Selecting one grade for everything can often lead to poor wheel performance and additional work requirements to clear up the damage caused during the cutting operation. If we look at the thermal damage effect between a poor cut compared to a good cut, we can see the image on the left is burnt and discolored. This is usually down to incorrect cutting wheel being used, or insufficient cooling, or cutting too fast. Cutting with the optimal cutting wheel for the material is the critical first step of sample preparation. So let's have a look how we select the correct cutoff wheel. It is important to choose the correct wheel for the material we wish to cut. Struers has made a selection guide which can be found on page 10 of the consumables catalogue and is currently shown on screen. In order to choose the correct wheel, you need to know, or at least have an idea of, the hardness of the type of material that you are cutting. Ideally, you'd need to know whether it is ferrous, non-ferrous, ceramic, or even plastic. If we look at the graph on the screen, on the x-axis we have the material or material group in question. On the y-axis we have the hardness of the material. In the table below the diagram, you'll find the Struers cutting machines and the standard wheel sizes, in which the wheel sizes correspond to that material. The selection guide is intuitive, and we generally aim for your material to be somewhere near the middle of the cutting wheel capability range. For example, if we choose a medium hard steel, which can be found in material group 5, and the typical wheel range we aim for has a hardness between 170 Vickers and 520 Vickers. If this meets the criteria that for the material we are cutting, the column directly below this tells us which cutting wheel would be the best option to choose. When we know what material class column we need, we can trace this column down to match up with either the machine that we're using or the wheel size we need. So if we think about cutting wheel identification, Struer's cutting wheel identification looks something like this. The first number indicates the hardness of the material we wish to cut. The harder the material, the higher this first number. Struer's currently uses 1 to 6, so this on the screen is a hardness range 3. The second number indicates any special features of the cutoff wheel. For example, in this one we have a 0, which means a high concentration of abrasives, and just as another example, 2 would mean a fiber reinforced wheel. The letter is the abrasive material used in this wheel. For example, A indicates aluminum oxide, S indicates silicon carbide, and D indicates diamond. The last two numbers are the size of the cutoff wheel in centimeters. If we take the Discaton 100 as an example, a softer non-ferrous materials would require cutoff wheels with an S for silicon carbide abrasive, and the size could be either 25 or 30. Ferrous materials would need the aluminum oxide abrasive wheels, and they would be identified with an A abrasive. Again, as it's using the same machine, the 25 or the 30 would fit this variant of Discaton. During cutting, a reduction in contact area can be a real benefit, especially for complex parts, as reduced contact area can reduce forces on the sample and on your clamping arrangement. Depending on the cutting machine we use, there are several options to reduce this contact area. On a wide range of cutting machines, ExiCut is this main option. This can be found in two forms, either by small movements in the cutting wheel or by small movements in a motorized cutting bed. This adjusts the sample position relative to the cutting wheel. In both cases, the outcome is the same and can be seen on the screen. Other advantages of ExiCut are less wear on the cutting wheel, less generation of heat, better for cutting large or hard components, increasing the cutting range of a specific wheel to allow harder materials to be cut with the same blade, within reason. AxioCut is an option available to larger cutting machines, the Axitom and the Magnetom. It is used for cutting extra large workpieces. On the Axitom, an additional 150 millimeters, which is 6 inches, of cutting capacity is available with the AxioCut step. This cutting mode allows cutting of deep workpieces when measured from the front of the machine to the back of the cut, and can be seen as pictorially on screen. On the Magnetom, AxioCut Sweep offers something similar in a slightly different form. It's generally used to increase the speed of cutting and give better wheel economy and a very smooth cut. In both these cases, the contact area is reduced and the forces minimized. And both of these options are allowing for very large workpieces to be cut that we would struggle without this option. It is often overlooked that precision cutting machines can also benefit from this reduced contact area. On the Acutom and Secatom, as long as using accessories, we can use a rotating or oscillating specimen to give us this effect. On a precision machine, the contact area is always smaller than the larger machines. This small contact area can put a high pressure on a localized area, but due to the thin cutting wheels used on the precision machines, we need to ensure that we do not rush the cutting operation, as this can easily break a blade. Cutting on precision machines should always be slower and more controlled than with larger machines, so the use of ExiCut to increase cutting speeds on these precision machines is not the aim. Typically, when using precision machines, we are looking for the best possible cut finish. Anything we can do to improve things will help us with the next step in the preparation process. If we have already mentioned that the use of ExiCut can be beneficial to the cut finish, so if we combine the precision cutting machine and ExiCut type features, we should be able to achieve a cut finish of less than 5 microns of deformation. This makes the grinding stage only a very fine grinding option. The clamping on these smaller machines we will look at later in this webinar. If we take a look at the positioning of your sample during cutting, ideally the sample to be cut will be clamped just in front of the center line of the cutting wheel movement. This ensures all the cutting force pushes the blade in the same direction on the downward part of the wheel rotation. If this is not the case due to clamping position or component geometry prevents this cutting in this sort of position, special care must be taken as the wheel will be pushing and pulling away from a component at the same time, which can cause vibration and movement of the component within the clamp. This is especially noticeable on some large or deep cuts. Also, if possible, the cutting wheel should approach the sample at 90 degrees. This will help keep the cutting wheel moving in a straight line and give the straightest possible cut. If the sample surface is at an angle, the cutting wheel will deflect slightly. If this happens, the wheel will not be able to straighten up by itself during the cut. If this situation continues, the wheel will cut further and further offline until eventually the wheel fails, or you cut into the cutting bed. Cutting too fast can also give this issue, with the wheel trying to find the easiest way through a sample, which can cause the wheel to wander. Again, this will either lead to wheel failure or cutting into the T-slot bed. If there is no other option but to cut on an angled surface, our advice is to start very slowly and allow the abrasive to cut a small notch in the surface to act as a path which should allow the wheel to follow during the rest of the cut. The list on screen outlines some of the common issues we can encounter during cutting. Poor clamping and cutting setups can lead to many of these, either in isolation or more often at the same time. Typically, the more complex the cut, the more chance of these events occurring. So taking the time to look at the sample you have clamped and work through in your mind what will happen when I make the cut. Do I have enough support once a piece is cut away, and am I cutting into a load-bearing section? Always take a moment to look at your setup before you start the cut. Once you press go, it's often too late. Care should be taken to ensure fragile specimens are supported and protected by clamping jaw faces. The use of rubber matting between clamp jaws or feet and the sample can give a few benefits, including cushioning from a hard face, flowing around a sample face that may not be uniform, and giving increased friction to prevent movement. Shaped and grooved jaws and feet, along with custom-made jigs for special applications, can be used to good effect when setting up a cut. The more often a particular cut takes place, the more we would lean towards suggesting setting up a jig for repeatability. Obviously, we can't cover everything in this webinar, so we've just picked several examples that either they often get raised with us here in applications, or were noteworthy as something that gave us cause to find a solution to a tricky problem. So if we look at our first example, it looks fairly simple. It's just a ring that we're trying to cut. But even simple looking cutting actions can sometimes need specialist clamping solutions. This large steel ring needed a sample cutting from a specified location around the circumference. However, whenever the first cut was almost complete, the internal stressors would collapse the ring on itself and grab the cutting wheel, causing the wheel to break. The image on the right clearly shows the challenge when cutting such a workpiece. Whilst there are several ways of clamping the part during cutting, using the readily available vertical clamps would be the most flexible for different size parts and allows easier maintenance and replacement should changes need to be made. Our particular solution involved using 4 standard vertical clamping tools in this case. Swivel shoes with angled feet were able to grab onto the inside edge of the ring to avoid this pinching effect. Using the standard flat swivel shoe did not stop this pinching effect, as the friction force alone was not sufficient to prevent movement of the part. This pinching effect can also be found in sections such as this one, where a part has a compressive force built into the design. This special pinch reduction clamp was designed to clamp in both the Y direction and twist in a way that creates an X-axis force to resist any tendency for the sample to collapse and grab the wheel. On this particular part, we've also added a support to the cylindrical shape with an adjustable support, which consists of a prism, which can be positioned on a base plate designed to drop into either 10 or 12mm T-slot bed. This solution is another off-the-shelf design and can be used in conjunction with the 3D line of cutting wheels that have a hexagonal pattern on the sidewall designed to reduce frictional forces on the side of a cutting wheel and allow coolant in to help reduce cutting wheel grab. A better view of the adjustable cylindrical support can be seen here, used for a very different part in its other orientation. Here it is used in conjunction with a standard quick clamp to give better support and allow the sample to be kept horizontal to ensure a perfect transverse cut. For samples with no flat sides, or where any flat sides are in positions that make standard clamping very difficult, these chain clamping tools offer an option. The chain forms around the circumference of a part and provides many clamping positions along the chain's length. These can be used in isolation against the cutting bed or in conjunction with adjustable supports, with or without crowns, that allow the sample to be lifted off the cutting bed and allow accurate alignment to ensure a perfect cut. Due to the flexible nature of both the chain clamp and the crowns, almost any sample angle can be achieved. Just keep in mind what we discussed earlier and take the intercept angle between the sample and the cutting wheel into account and proceed accordingly. The crowns used with the chain clamp can also be used with standard vertical clamps. Here we see 2 different setups showing variable height adjustments and the swivel shoes designed for cylindrical parts. Raising parts off the cutting bed can be very useful, but will also require the use of riser blocks for the vertical clamps. A variety of vertical clamping tools for complex shapes where there may be no parallel sides to clamp onto that we can use when using the quick clamps are available for all T-slot sizes used. Riser blocks for both 8 and 10mm clamps increase the height by 65mm and the 12mm clamp by 75mm. Extension arms increase the reach from 60mm to 135mm on the 8 and 10mm clamps, and from 70 to 150mm approximately on the 12mm T-slot clamp. The sliding block is available for the 12mm option to increase flexibility as the user is not tied to the T-slot positions. A recent difficult clamping job that we had here at Struers was sent into for the applications team to optimize and prove capability for accurate sectioning of a pie-shaped slice from a gear wheel on this assembly. The sample had to be removed from a larger part before sectioning the desired piece, which required the use of support blocks to level the sample. A quick clamp to hold onto the sample in position and a vertical clamp with riser block to prevent the whole clamping arrangement collapsing during and after the cut had to be used. Once the desired gear was removed from the part, the use of two vertical clamps was used to hold the sample in place during the next cutting operation. As there was no compressive stress in this component, there was no reason for the use of additional clamping tools or devices. However, there was still very little surface area to clamp onto, so the swivel shoes were removed to make the contact patch on these vertical clamps smaller. With this setup, it was straightforward to cut the sample, rotate, and cut again to remove the pie slices for examination. Custom fixtures or jigs can be made and let me start again. Custom fixtures or jigs can be made and can be of great advantage, especially when carrying out routine cutting on complex and difficult to clamp shapes. The time saving found once a jig is made can far outstrip the cost of making it in the first place. Here we have an example of a sample where very little sample is available to clamp onto and hold in position during cutting. A customer made a custom jig which allowed us to clamp onto the very small areas on each corner of the part without distorting it and also keeping it in place. This particular jig can also be rotated. As we can see from the slide, the laser attached to this cutting machine can be used to check the position of the cutting wheel before we attach either the part or the cutting wheel. The jig is designed in such a way that the part does not need to be unclamped between each cut, saving time and increasing throughput, whilst keeping the sample safe and secure. One of the largest cutting machines available recently had an upgrade and included the option of a rotating cutting bed. This new design allows cutting over the full area of the T-slot bed. The custom clamp shown here was made to ensure that each part of this complete crankshaft was supported to allow the desired parts to be removed without the need to unclamp and reclamp after each cut sequence. The rotating bed was used to allow each end to be sampled, whereas standard X table may not have the required travel to reach all locations. In addition to this custom clamp rotating bed providing a solution for a complex shape, the use of intelligent measuring can ensure the cutting wheel travels far enough to cut the sample, even taking wheel wear into account and optimizing the wheel RPM to provide the best available cutting conditions. This sample caused particular problems as it has no available straight edges, very small cross sections and complex geometry. A longitudinal section was required through the ball end into the stem. The full length of the stem was not required. A plate was made with cutouts and depressions to locate the part and allow the use of a single vertical clamp to keep the sample in position during cutting. As you can see from the top left image, care has to be taken during this first cut to ensure you do not cut through the clamp. The use of automated cutting options allows accurate cut length to be programmed on all of our automatic machines to ensure that this sort of mistake should not occur. Again, the use of the laser for alignment greatly assists in positional accuracy and is reflected by the quality of the result. This challenge of cutting a spherical ball which contained cemented carbide required an out-of-the-box thinking solution. The solution used actually makes the cut quite simple to complete in the end. Due to the shape, it is difficult to fixate or clamp during cutting with almost any clamp available. In addition, the hardness of the material made it very difficult to clamp and hold in position during and after the cut. The solution we found was to mount the ball in Replifix before cutting. This made it possible to clamp and cut more easily with a standard quick clamping tool. The Replifix was easy to remove after the cut to retrieve the sample. The jaw blocks used for quick clamps can extend the range of capability to allow more complex or troublesome cutting requirements to be carried out. Prism jaw blocks exert a slightly downward pressure to keep round profiles pushed onto the table during cutting and provide a more stable setup for samples such as bar stock. Thin wall tubing can easily be deformed during clamping, as often the force needed to hold the sample in place is higher than the strength of the part. The use of rubber-coated jaw blocks allow the rubber to deform around the sample and spread this clamping force over a larger area, helping to prevent damage to the part. Grooved jaw blocks use the grip generated by the grooves to provide more friction to the clamping setup, helping eliminate slipping of the sample. This is especially useful if the sample is hard-faced or made of harder and smoother materials. Occasionally, a sample required from a component involves changing the angle of a cut. A turntable for angled cutting can be used in this case, with accurate positioning between 0 and 90 degrees, which can also be locked into position for repeatability. As you can see from the screen, these turntables use the same T-slot design and allow the use of any of the clamps that we've already mentioned. If we look at a smaller sample, such as this washer with HVOF coating, this needed to be sectioned by cutting and then mounted and prepared for further metallurgical investigation. The challenge was to perform the cutting without introducing cracks or delaminate the brittle coating. The cracks can be seen on the screen. The customer had experienced cracking of the coating, and our challenge was to assist the customer to work out if the cracks were pre-existing cracks or formed during the part of the preparation process. The prime suspect for us was the manual cutting process causing excessive stress on this coating. When cutting small samples, it is very difficult to obtain consistent low feed speeds. With samples this small, the resistance offered by a small sample will be so low that cutting slow enough in a controlled manner is almost impossible time after time. Part of our plan was to have a robust process that can be carried out repeatedly with the same perfect outcome. Variability is not an option here, as the wrong result can cause ripples in the production line, causing delays and lost revenue. For this sample, we used a two-part solution. It was determined that the problem stemmed from incorrect cutting parameters. The cutting was carried out with too high a feed speed. With this being a manual operation, as stated in the previous slide, it was decided to move this cut onto an automatic cutting machine. In addition, due to this sample being very small, the decision was made to use a precision cutting machine, which allowed very slow cutting speeds. In this case, we used 0.1 millimeters per second. During discussions with the customer, it was also found out that cutting was sometimes carried out incorrectly, so the coating was being pulled away from the main body of the material. Education of the operators to ensure coatings are always supported during cutting means that the coating will be on the top surface during a cut of this type, allowing the bulk of the material to support the more brittle properties of the coating. A trial was carried out where the sample was mounted in an epoxy resin prior to cutting. This mounting had two benefits. We could use vacuum impregnation, which would show us if there had been any damage prior to any preparation, and also support the coating during cutting, making it more likely to resist fracture. In the images on screen, we added EPO dye to the resin, which gave us an excellent contrast between the coating and the resin. If any cracking had been present before cutting, the vacuum impregnation would have pulled this resin into the gap left by the crack and proved a pre-existing crack of the coating. Another consideration we had to make when we cut the coated samples is what cutting wheel to choose. If the whole sample was made of the coating material in this case, we may well have just used a diamond cutting blade. However, with the bulk of this material actually being steel in this case, it would cause unnecessary damage to a diamond blade. So we're forced to choose between an expensive diamond wheel we know we will damage, or an abrasive wheel that will have a high wear rate on a very hard coating. After mounting the sample, this choice is removed, as the bulk of the material on a mounted sample, such as this, is now plastic. As such, the best blade option is an electroplated diamond blade. This electroplated diamond blade is designed to cut plastic samples and resist getting the abrasive clogged. In addition, the electroplating should minimize the damage we can expect when cutting the metal. We do need to state, though, that cutting steel with diamond wheels is not desirable under most circumstances. The challenge we've had a few times is sectioning of spark plugs for quality checks. The dimensions of spark plugs do not allow typical clamps to hold onto the part securely enough, as the top and bottom of the spark plugs do not have the required cross-section to clamp onto, and also the electrode can be damaged if you clamp this way. A vertical clamp on its own doesn't give the required clamping force to keep the sample stable enough during a longitudinal cut, and so a custom holder is used, as shown in the slide, to assist spreading the clamping force and keep the plug where we need it to be for this cut. It also allows the clamping position to be much nearer the cutting axis, as shown on the left-hand image. Precision is key when carrying out such a cut such as this, and so the precision saw was used due to the thickness of the blade, allowing us to position the clamp very close to the cutting axis. The complexity in this case is amplified by the variety of materials in the spark plug, with metal and ceramic being in the same part. We use the diamond blade for this part because the ceramic part would be just too hard for a standard abrasive wheel. It is important to note that when using diamond blades, we use the stay function when cutting to prevent potential damage to the diamond abrasive when retracting the wheel. It is common to see bolts and fasteners sectioned longitudinally for evaluation purposes. Whilst there is merit to the mount and grind to center method, there is, however, a clamp for use on the Cecotom that allows bolts and fasteners to be cut without mounting, to give accurate and simple sample sections. This bolt clamp will allow a longitudinal cut to be made without pinching the blade. Various options on the clamp allow for angled and flat type bolt heads, and a blade guide can be fitted to keep the blade from wandering if a small flange set is being used. As a quick recap, for all cutting machines with a T-slot table, no matter which size of T-slot, there are a wide variety of clamping tools to cover almost every eventuality. Sometimes having the additional clamping set toolbox, shown here at the bottom left, for the 10 and 12mm T-slots may be required when building one-off clamping solutions for difficult to hold jobs. The precision machines and machines using a fixed stand, shown here on the top left, can use the dovetail clamping system. These small clamps have been designed to meet the demands of small, intricate and complex samples. A fixed stand is available in 10 and 8mm T-slot versions to allow any of the dovetail clamps to be fitted to all but the two largest machines. These clamps have been developed to be used as similar to qualified tooling as you find in a CNC profiling machine. What this means is that your small sample can be clamped up away from the machine and inserted into the dovetail fitment. When satisfied that the sample is held securely, the dovetail clamp and sample is attached to the machine for cutting. This gives large benefits when cutting similar parts over and over, as additional clamps can be set up as one is automatically being cut and exchanged quickly for an almost continuous throughput. Using the fixed stand and the dovetail clamping system, we can see a small turbine blade clamped securely for cutting on the Cecotom 6. The fixed stand and CATSI clamp allow for unusually shaped components to be positioned in a way as to allow the blade to be cut at an optimum angle, allowing the best cut speed versus contact area setup. The Accutom is designed to only use the dovetail clamping system. An example of a recent problem applications had to solve was how to section a human tooth and tooth implant to give micro-tensile specimens for testing. The problem here is that the tooth and implant would be too brittle if you clamped them by a metal edge on many of our clamps, and they also naturally do not have any flat edges to clamp onto. As you can see, each sample was mounted in a cold setting acrylic, which we used to clamp onto to prevent damage and allow any shape of finished parts to be used to make the clamping operation easier. On the left, we can see the tooth in its acrylic mounting compound clamped in a Cachera dovetail clamp. The image on the right shows the same clamp used in conjunction with the angled Catjo clamp to allow us to cut directly into the face of the tooth. The clamp was positioned so that we could cut using the multi-cut function to get accurate, perfectly positioned slices in both the X and Y direction to make very small matchsticks of tooth. The image on the right clearly shows the level of accuracy we can achieve even with a difficult to hold sample such as this tooth. The clamp was then positioned back into the original orientation and the sticks were cut from the main body of the tooth, giving us these micro-tensile test pieces as required. A full webinar on this subject was recently presented, and if you're interested to know more, you can still download a copy of the webinar from the Struers main website. And I'll give you details on how to find that shortly. In order to avoid most problems during materialographic cutting, the following rules of thumb should be adhered to. Use of a suitable clamping solution with the right clamping tools or jig. Optimize the feed speed and the wheel speed if possible. Use of the correct type of cutoff wheel. Use of a suitable cooling system with sufficient cooling liquid. And if necessary, the use of special clamping devices and jaws. And remember, if you can move your sample after you've clamped it, the chances are it will move during the cutting and break a cutoff wheel. If in doubt, give it a wiggle. If you'd like to know more about cutting, clamping, and other technical information covered in today's webinar, feel free to check out the Struers knowledge section on our main website. You can find out who your local application engineer is in the knowledge section, or if you're in the United States, just email us on lab@struers.com. Product information, safety datasheets, and product datasheets are all available from the library section on the main website. You can find information on previously recorded webinars on a variety of topics in the webinars and courses section, as well as find out what's coming up and how to sign up and join in. I'd like to personally thank everyone for joining me today, and if you have any questions, you can use the WebEx tool to send them to us here. If we don't have time to answer them today online, we'll email you very soon.
Thank you, James, for a great webinar. Now comes the Q&A portion of the event. A few questions have already come in, but if you would like to ask James a question about today's webinar, please use the Q&A window. Okay, give people some time to write out their questions. Okay, good. Question number one, I suction composite samples, and I'm not sure which cutoff wheel to choose. Do you have any guidelines for choosing wheels for composite materials?
Okay, so there's two angles for this. Are we interested in more than just one part of the composite? If not, then we can choose a wheel design to give the best cut for the interesting part. If we do need to view the whole thing, then we've got to take a view and use a cutting wheel that's going to give us a satisfactory cut across the whole thing. But you've got to bear in mind the hardness of all the components involved. If there are some very, very hard components in there, you're going to need to really take those into account. You can't cut through things like tungsten carbide very easily with aluminum oxide cutting discs. Occasionally, if your very hard material is very thin, we can probably just about get through it, but sometimes you may need two different cutting wheels to do the same job. So you will cut through one part of the material with one cutting wheel, then bring the wheel out of the cut, change the cutting wheel, and re-enter the cut with a different blade to finish off. I hope that helps.
Okay, so question 2. I sectioned copper pipes in my lab in Acetone 15 and didn't realize you recommended an additive for the tank. Which additive should I use for my copper pipes? This would allow.
Okay, so if you're cutting copper and you're only cutting copper all the time, then we recommend the Corozip CU. This is formulated for use in our machines, and it stops this. There's a kind of galvanic cell that can take place between the frame of the machine and the copper debris that kind of floats around in the tank. So we use this Corozip CU, and it kind of stops this reaction from taking place. Um, uh, yeah, so apparently it's a galvanic process, and this addition will stop this from occurring, so it prevents damage to your machine. So it's not going to change the way it cuts, but it will prevent damage to your machine. So it's a good option to go with that.
Sounds good. Hello, James. Are there any accessories / tools to make the PCB cut?
On well, personally, I would. It depends on the size of a PCB that you're using. Generally speaking, if it's a full-size board, then I would be using a vertical clamp with rubber underneath the jaw to protect your sample. Holding it in place is going to be a little bit tricky, and again, this is all depending on the size of the PCB. They range in sizes. If you've got really big components and you're clamping only in one point, then you've got quite a pivot point, and it may try and twist, which is not something you want to happen. So you may need multiple vertical clamps to hold this in position. If the PCB is small enough and you have a small precision machine, the use of the precision the clamps for the precision cutting machines is quite a good option. They can hold very, very small, very complicated shapes quite easily. And as I said in the webinar, if you don't have one of these precision machines, you can use a fixed stand and a dovetail clamp to using all but the magneton and the Acetone. So there's plenty of options out there.
Give a little bit more time for some additional questions to come in. Please don't hesitate to type question for James. We have plenty of time. type of rubber would you suggest for clamping?
Um, that's a tricky one. The the rubber we have in the lab is just something we've kind of had lying around. It's just a general silicon rubber, something that's going to be flexible enough to form around any components we want to protect. Bizarrely, in the past I've used mouse mats. You know, the old type of mouse mats with the foam backing. They actually work really well as feet for these clamps as well, because that spongy stuff that used to be attached to things flowed round components quite well as well. So those are a couple of options that we would use, but we don't have any standard rubber that we go to. It's just whatever we have laying around. The inserts for the quick clamps, the rubber in those is just a standard black soft rubber that we don't get a say in. It's just what it is.
So this goes back to your composite answer. Someone else wrote in saying they have the same issue with carbon composites that also include a hard resin. Kind of trying to figure out which kind of cutoff wheel, I would imagine.
Okay, so um, in cases like this, you have the very hard carbon and the quite hard resin that's in there. So we would always recommend the electroplated diamond wheel for those. So it would be an E, a wheel with a prefix E. If you're using a precision machine, for example, on the Seekaton, we would probably use an EOD20. That's an electroplated diamond wheel, 200 millimeters. They're about 0.8 of a millimeter thick, and they should cut carbon composite quite easily.
Same person who asked about the PCB was kind of curious on cutoff wheel suggestions, kind of what type should he be looking for?
Okay, it's very similar to the carbon composite. You've got a lot of plastic involved in PCBs. So again, the electroplated diamond wheel is pretty well suited for that. It's also going to cut through any components that you've got in there. A lot of PCBs contain ceramic components, and this diamond wheel will cut through all of those. You need to make sure that you are, because you're cutting quite a bit of plastic involved in these and copper, you may block the cutting wheel. You may fill in any of the pores that are in there and block the diamonds. So you need to be making sure that the cutting wheel is dressed regularly. Each cutting wheel will come with a dressing stone. And to dress them, we would just suggest clamping up that cutting stone and just cutting a slice off the end. That should keep them in tip-top condition.
Thank you. Final question. Any suggestions on clamping a shaft with a larger radius section than the rest of the shaft is a smaller diameter, especially when needing to cut various places on the shaft?
Uh, I think the use of the crowns to lift the whole shaft beyond that larger diameter would probably be the best option you've got. As long as I'm picturing what you're describing correctly. Clamping with the vertical clamps, as one of these slides showed, with a profiled foot directly above these crowns, should be able to keep everything nice and secure during the cut. The chain clamp could also be used in this case, but yeah, you would need quite a few crowns, I would guess, to raise the whole thing and make sure it's all nice and level. They're all individually adjustable, different heights to make sure that you can get that. So it's not like these crowns come in in a few different sizes. They all have a thread that you can actually increase or decrease the position individually.
And that concludes our Q&A round. If James did not answer your question, he will be following up with you personally. So please join me once again in thanking James Sylvester for presenting today. And as you leave today's webinar, please take a moment to fill out the survey. We appreciate hearing from you and have a lovely day.